Okay, so many thanks, Edward, for being among us within the thematic session. Professor Edward Lee has been working in embedded systems for more than 40 years now. He graduated from Yale, then made a detour through MIT, and then ended in Berkeley, where he is now an emeritus professor in the grad school of the Electrical Engineering and Computer Science Department. So the research of Professor Lee is focused on cyber-physical systems. He's the author of many leading textbooks in the field, myself included, I do use them. And recently he has been writing philosophical and social implications of technology books, like the first one running 2017 was Plato and the Nerd, the creative partnership of humans and technology. And the most recent one is the co-evolution, the intended futures of humans and machines. So thank you again, Edward, for being among us, and please.
Thank you, Chadlia. So just as a little bit of background, Professor Gerard asked me to give a fairly high-level talk, which I actually very much appreciate the invitation, because it sort of forced me to step back and look at a lot of the ideas that I've been pushing and that have been driving my research from a fairly fundamental perspective. And so it's really kind of nice to, be asked to step back and look at things from the big picture perspective. So hopefully this will be meaningful, as meaningful to you as it's been to me to prepare this. Let's hope. So anyway, the topic for today is, as I said, pretty high level. So we're looking at the issue of science and engineering for cyber-physical systems. And I'd like to start by just kind of telling a little story. I got approached a few years ago by a company that I won't tell you exactly which company, but it was a company that's involved in industrial automation. And they were interested in the problem of virtual prototyping. So what they wanted to do was to be able to create simulations of factory automation systems that would be accurate enough that they could configure the system in simulation and have a reasonable confidence that it was going to work when they actually built out the hardware. And these are pretty complicated systems. So, this image is from a factory that where Volkswagen makes an electric car, and there's quite a few robots that you can see here, and they happen to be controlled in this case using Siemens technology, but there's several other vendors that provide infrastructure like this. So the problem that this company was having was that their simulations weren't accurate enough, that they were missing key properties of the behavior, mostly of the software. And they came to me asking if we could help them improve the accuracy of the simulations. And I told them that we couldn't help with this. And moreover, I told them that I actually thought that wasn't the right approach, that improving the accuracy of the simulations is essentially an impossibly difficult task. So why is it impossibly difficult? Well, if you're looking at the behavior of software as it interacts with the physical world, which is the essence of cyber-physical systems, then you have to be concerned with the timing behavior at a very deep level. And timing behavior is not really expressed in software. And it's affected by many things that happen in the system. It's affected by network effects, so contention over the network, the routing of messages through the network, buffer overflows in the network. Within the individual microcontrollers or microprocessors, it's affected by the architecture in the microprocessor, caching effects, pipeline hazards, interrupts. The operating system, whatever operating system you're using, is going to have an effect on the timing. And often these timing effects are very difficult to characterize. So my claim is that it's really essentially impossible to construct an accurate model of such a system that's going to deliver the level of virtual prototyping that you need in order to be able to actually have confidence in how this system is going to work when you integrate the software with all that hardware. So what is the alternative, right? I'm not saying that virtual prototyping is not a reasonable thing to do. Another term that people use these days is digital twins. You'd like to have a digital model of your physical system, and you can use that for any number of purposes, including virtual prototyping, but also you can use it for anomaly detection, for preventative maintenance, for all kinds of purposes. So the question becomes, okay, if constructing accurate models at this level is essentially impossible, how can we accomplish the goals of digital twins and virtual prototyping? So when I was working on my first book, Professor Gerard mentioned that I've written a couple of books that are focused on kind of the philosophy and sociology of technology. And when I was writing the first one, I got an insight that was new to me, and I was very surprised that it was new to me, because in fact, it had this insight had actually been, I think, kind of in the background governing my research, my approach to research for my entire career. But I didn't know it was there, and I had never articulated it before. So I'd like to share that insight with you, because many people find this surprising. And of course, those of you who have heard me talk about this before won't find it surprising, because you've heard me talk about it before and you've probably fully internalized it. And it's one of these insights that I think is obvious in retrospect. But if you haven't really thought about it, it can be a bit of a surprise. So what is that insight? Well, these virtual prototypes that we're talking about, if we want to build a virtual prototype of a factory floor, we're talking about building a model. A digital twin is going to be a model of that factory floor. So what is the value of a model? Well, in science, the value of a model lies in how well its behavior matches that of a physical system. What a scientist does is construct models that emulate physical systems. But that's not really what engineers do. So in engineering, the value of a physical system lies in how well its behavior matches that of a model. So if I give you a piece of silicon, the value of that piece of silicon lies in how well it behaves like the logic diagram. Okay, the logic diagram describes, it's a model, okay? But there's a sort of, I mean, these are kind of duals of one another. There's for a scientific model, it's incumbent on the model to match the physical system. For an engineering model, it's incumbent on the physical system to match the model. So another way to think about this is that a scientist asks, can I make a model for this thing? And an engineer asks, can I make a thing for this model? So let me give you a very simple example. All right, so suppose you've got some physical system like this. I actually have this right here. This particular Newton's cradle. If you can see a video of me, okay. I bought this on Amazon for $6, including shipping. All right. Now you could construct a model of this using Newton's laws, and the model is this mathematical framework that has a description of what the behavior should be. Right. You could use that model to come up with a simulation, for example. So you might be, this is your virtual prototype, okay, of your factory floor. But the physical system that I bought on Amazon doesn't really match that model very well. I mean, look at it. It's a piece of junk, actually, you know, and I think it's very cheaply constructed, and there's the length of the fibers that hold up that are used to hang the balls are not all the same, and so it really doesn't work very well. So it doesn't really match that model, and so this is kind of the scenario where you try to construct a digital twin, and the digital twin is actually not very useful because it's not describing the behavior of the system very well. If you're thinking of this model from a scientific perspective, then it's the model that's flawed. But if you're thinking of it from an engineering perspective, it's the realization that's flawed. Now, of course, the reality is that both of them are flawed. Any scientific model is imperfect. Any physical realization is imperfect. But the emphasis is different in these two perspectives, okay? So I'm an engineer, and I tend to focus on engineering models. And the question here, with regard to the digital twinning problem and the virtual prototyping problem, is that maybe we should try to be making the realization of the factory floor more faithful to our models rather than the other way around. So in other words, we should construct a model of the factory floor that is explicit about the timing, for example, and then we should make sure that the software and network delivers the timing behavior that is specified by that model. If you can do that, then your digital twin will in fact be faithful to the model, I mean, to the physical system. So one way to think about this is there's a famous quote from George Box that was published in a paper that he wrote with Draper in 1987, where he said, essentially, all models are wrong, but some are useful. Many people have heard this quote. It took me a while to realize that George Box here was talking about scientific models, where it's incumbent on the model to match the physical reality. But there's a mirror image statement that is essentially all system implementations are wrong, but some are useful. This is where it's incumbent on the physical realization to match the model rather than the other way around. And these statements, of course, are both true. All scientific models are an imperfect description of what they model, and all engineering models are an imperfect description of what gets realized. Or put it a different way, and perhaps more accurately, what gets realized in the physical world is an imperfect realization of the model. So we can start to associate a few key concepts with this. So a scientific model is faithful if every property of interest that it exhibits is also a property of the system being modeled. Okay, so this is a fairly carefully constructed definition of faithfulness. Every property of interest. Well, what is a property of interest? Well, you know, a property of a model that may not be of interest is what kind of paper it's written down on. That is a property of the model, but it's not a very interesting property of the model, right? So you have to focus on interesting properties of the model. So if a model exhibits some interesting property, some property that you're actually interested in, if that is also a property of the system being modeled, then we call that model faithful. For engineering models, we turn things around and we talk about the correctness of an implementation. So an implementation of a system is correct if it exhibits every property of interest of the model. So for example, if I give you a logic diagram or a VHDL program for an integrated circuit, then the piece of silicon that realizes that is correct if the piece of silicon exhibits every property of interest of the VHDL program or the circuit diagram, okay? You don't need to worry about properties that are not of interest, like how the VHDL is written or things like that, okay? Um, Faithfulness and correctness are never perfect, right? Every physical realization has the potential to deviate in behavior from any model that you give for it. Any integrated circuit will fail if the temperature of its environment exceeds its operating range. It'll fail if you immerse it in salt water. There's all sorts of circumstances in which it will not behave like the model. So correctness and faithfulness are never perfect relations. So a piece of silicon that doesn't behave like the model, however, is really fundamentally not a very useful piece of silicon. But integrated circuit design, I think, it's sort of my canonical example of the real power of engineering models as opposed to scientific models. Right? This is an image of a chip. This is actually several years old now, but each of these dies, there's a couple dozen dies on the screen there. Each of those has 1.4 billion transistors. Our ability to construct a system of this intricacy and complexity is very heavily reliant on this engineering use of models. We build an engineering model for this system, and then we make the silicon conform with that model. Now, of course, scientific modeling plays a huge role in being able to make chips like this, of course. One of the key roles it plays is in helping us determine how to make the silicon behave like the physical model, like the engineering model, right? It also plays a role in determining under what circumstances will the physical realization deviate from the engineering model. So for example, a temperature range. You could use a scientific model to determine at what temperature will the silicon start to melt. And at that point, you can probably be fairly sure that the silicon is going to start deviating from the engineering model. And you can use a scientific model to determine at what point that will occur. So the use of engineering models and scientific models is rarely exclusive. In fact, almost any interesting project will involve both engineering models and scientific models. But the point is that these models play very different roles from one another. So there's a number of other very successful examples of engineering models. I think computer programs are in fact engineering models. They are specifying, what are they ultimately specifying? Well, they're ultimately specifying how we want electrons to slosh around in silicon. That's really the specification. They're a very abstract specification of that, and we have developed technology that delivers physical systems that are astonishingly faithful to those engineering models. We can write programs that execute 1 billion instructions per second without error for years. That's a pretty remarkable faithfulness. I mean, it's a correctness and faithfulness, both, right? The model is faithful to the realization, and the realization is correct in that it does in fact deliver the behavior specified by the program. Not perfect, never perfect. Okay, that relation between the physical realization and the model is never perfect. But in the case of integrated circuits, it's astonishingly good. So there's another insight that I got once I understood this distinction between these uses of models. I went to a conference that was organized by the National Science Foundation in the US, and it was pulling together a lot of top experts in robotics to address the specific problem that simulation of robotic systems tends not to be very useful. Okay, that was the whole theme of this conference, is that when you simulate a robotic system, everything seems to work. And then you deploy it in the physical world and it doesn't work. And so the sort of catchphrase that kept getting used during the course of this conference was simulation is doomed to succeed. And I think that I came to the realization that this statement is actually confusing engineering models for scientific ones. So how could that be? Well, let's dive in a little more deeply into this relationship between models and between models and physical things. So I'll talk briefly about what is really a mathematical property. So if you have an abstraction A of some model B, we say that that abstraction is sound if every property of interest that is true of A is also true for B. Okay, that notion of soundness of an abstraction is a key notion. And this is an asymmetric relationship. So if A is a sound abstraction of B, then we say that B is a refinement of A. Okay, in a sense, you can think of it as a model B has more detail than A. So to give you a concrete example, if A is a chunk of C code in the C programming language, and B is a chunk of assembly code in x86 assembly code, right? Then the C code is a sound abstraction of the assembly code if every property of interest that is true for the C code is also true for the assembly code. So for example, a property of interest might be, what is the sequence of variable assignments to some variable in C? It starts with some value and gets incremented to some other value, then gets incremented to a third value. If that property is also true of the assembly code, then the assembly code, then the C code is a sound abstraction of the assembly code. We use a compiler to generate the assembly code. You don't usually do this in the scientific way where you construct the abstraction by hand from the refinement. We do it the other way around in engineering. We construct the refinement from the abstraction using a synthesis process like a compiler, okay? So in the context of simulation, when you do a simulation of a system, you're always working with a model of that system. So a simulation is driven by a model. So a simulation of some model A is doomed to succeed because it cannot reveal properties of a refinement, nor in fact properties of the physical thing in itself that are not also properties of the simulation model itself. Okay, so for example, if you're trying to simulate a robotic arm and you don't include in your model the inertial properties or let's take specifically, the fact that the metal construction of the robot arm bends a little bit when the robot arm moves. That's maybe not included in your simulation. It's not in your model, okay, that drives the simulation. And consequently, that simulation cannot possibly reveal that property. It simply won't reveal itself through that simulation. And so this is essentially the problem that a simulation model is doomed to succeed, because it's just going to tell you about the model, not about the thing in itself. So this abstraction and refinement is, as a mathematical concept, is a relation between models, not a relation between models and things, okay? The soundness of an abstraction is sort of an absolute property, whereas the relation between a model and a thing is always imperfect. Okay, abstraction and refinement can be perfect in a mathematical sense. So relations between models are in fact the domain of mathematics. And so we can put together kind of a very audacious slide that pulls together science, engineering, and mathematics all in one slide, okay? So we have the physical things at the bottom. These are physical artifacts, a mechanical robot arm with a microcontroller driving it, okay? That's a physical thing. We can construct a scientific model of that where it's incumbent on the model to match that physical thing. So if we're interested in the dynamic behavior of that robot arm, maybe this scientific model really does need to model the bending of the metal when the robot arm moves. An engineering model, however, works in the reverse way. If we construct an engineering model of what we want the robot arm to do, then it's incumbent on us to build the physical thing such that it does that. Okay, that's a different goal. It's a different procedure. So if you talk about an abstraction kind of works in the same direction as a scientific model. It omits detail from the lower level model, just as a scientific model omits detail from the physical thing. Okay, but the soundness of that can be given as a mathematical property, and consequently, you get this fairly complete picture now of science, engineering, and mathematics and how they interplay in the design of systems. Okay, so for this original problem that I talked about, the problem of constructing a faithful model of some factory floor is the question whether the models describe the thing in itself faithfully. Well, that's the question that this industrial automation company wanted me to help them solve. Okay, and my response to them was, it's the wrong question. The right question is whether you can build a factory floor where the behavior matches that of your models with high probability. And then doing virtual prototyping and digital twinning is really pretty straightforward, because it's incumbent now on the physical thing to match that model. Now, of course, it'll never match it perfectly, right? You can't, the relation between models and physical things is always imperfect, whether you're working in the science direction or the engineering direction. That imperfection has to be dealt with in any practical scenario. And your goal needs to be to reduce that imperfection to a tolerable point. You can never eliminate it. So how does this affect people in practice? Well, here's a model of an Airbus A350. So this was, I saw this when I was in Toulouse 3 or 4 years ago. I got a little tour of their facility there. And this maybe doesn't look much like a model, but it actually is all the parts of an Airbus A350, except for the parts that you usually see. Okay, it doesn't have the fuselage skin. It doesn't have the seats in the passenger compartment, but it's got every wire that the A350 has at the same length as the wire of the A350. It's got it's got hydraulic tubes with the exact routing. So it's rather odd to look at, because you'll see a hydraulic tube that seems to be bending around something, but they didn't bother to include the something that it's bending around because they don't need it for the model. So this model is a non-digital twin of an Airbus A350. It's a pretty useful model. They use it for detecting anomalous situations. So they use it for fault detection. So for example, they can simulate a subsystem failure and see how the rest of the system behaves. They actually power this thing up with a simulation of a aircraft engine. Okay, there isn't actually an aircraft engine in there, but rather they have an electric motor that simulates the turning of the turbine in the engine, that then drives an electric generator, which is an exact copy of the electric generator that's used to generate the power source for the A350. Okay, so they simulate the engine driving a generator, and then the generator is real and the electrical distribution is real. So this photograph is actually surreptitious. I should have included it in the photograph, but right below the photograph, there was a railing and a sign on it that said, "No photos allowed." And so I asked my tour guide, I see the sign, it says no photos allowed, but can I take a photo? And he said, well, not if I see you do it. And then he turned his back to me and I took a picture. So anyway, you can't obviously tell any secrets about Airbus from this picture. But this way of constructing models is really maybe drives home a serious limitation that scientific models have. Okay, one of the goals of this model is to be able to accurately represent artifacts in the implementation, such as the propagation of electrical signals through wires, right? Those have a certain delay, and that delay depends on the length of the wire. So in this case, they could have constructed a model of electrical propagation in a wire, but that turns out to be a pretty computationally expensive model. So it's really much more straightforward to just put a physical wire there and treat that as the model. Okay, so this is a fundamental limitation with scientific models. If you try to construct a simulation model of this by writing down all the differential equations that describe electrical propagation in wires, hydraulics in tubes, mechanical stresses, and so forth, you're going to have a hopelessly intractable computational problem, but it's also probably not going to be very accurate. There's too many parameters to tune, and the odds of your getting the parameters right are pretty small. So this is a fundamental limitation in scientific modeling, but we don't have the same limitation in engineering modeling. If, for example, we design the networks over which signals are propagating over wires in such a way that there is an engineering model of the delay through the network, okay? If we have an engineering model of that, and we can assure that the realization of the system with high confidence behaves like that engineering model, then we can use that engineering model. It can be a simulation model. It can be a software model. It doesn't have to be a physical model like this. Another implication of this is something that I learned quite some time ago. I first heard about this phenomenon from an engineer who was working for Boeing, who had worked on Boeing's 777, which was their first fly-by-wire aircraft. So in fly-by-wire aircraft, you have all of the mechanical surfaces, like the rudder and the ailerons and the flaps on the wings, are controlled over computer networks. The controls are mediated by computers running software, and in more old-fashioned aircraft, these are actually hydraulic or mechanical linkages that are driving those controls. So this Boeing engineer told me that Boeing expected to be making the 777 for about 50 years. And he told me that Boeing bought a 50-year supply of the microprocessors that they expected to use in the airplane. They made sure that those microprocessors were all made within a few days of one another on the same production line, so that they had similar physical properties. An engineer at Airbus that I told this story to several years later confirmed this story and told me that at Airbus, they actually store the microprocessors in liquid nitrogen to keep them from aging, because they're worried about the shelf life of these microprocessors. Now, why would an aircraft manufacturer have to do this? Well, it's because of an inadequate use of engineering models. And the fact is that they don't have this assurance of a physical realization matching an engineering model. And as a consequence, the only assurance they have of the behavior actually matching the design is if the physical realization is the same for every instance of the design. okay? If you're using engineering models, you don't need every physical realization to be the same. I can give you a very concrete example. The x86 instruction set. It's quite old, right? It's been around since the 1980s, maybe late 70s, and it still works. And the silicon on which it runs today is radically different from the silicon that it originally ran on. And yet, an x86 program will do the same thing that it did on the silicon 50 years ago. That's the power of engineering models, and that's what was missing and is missing, in fact, in this context of this aircraft system. Now, this is a cyber physical system, and so one of the key properties, one of the key reasons for this limitation, this kind of flaw in this whole process, is timing. The fact is that the abstractions that we use in computing, for the most part, do not express timing. There's no timing in the engineering model. And as a consequence, the timing is an emergent property from the physical realization. And therefore, if timing behavior matters, what you're going to get is simply, if you have to match the timing behavior in all your physical realizations, the only way you have to do that is to ensure that your physical realizations are all identical. Okay? So what should we do with this virtual prototyping problem for a factory floor? Well, one of the key things is to build engineering models that are much more explicit about timing. So in other words, again, we need to change the question, right? So is the goal for the model to accurately reflect the timing of the implementation? Or is the goal for the implementation to accurately reflect the timing of the model? And my claim is that if you take the second goal, then virtual prototyping, digital twins, and simulation all become useful. Okay? So I can turn these observations into a set of guidelines for goals that you should have in any engineering process, right? So one simple one, engineering models should express all properties of interest. That seems kind of obvious, but it's completely missing in cyber physical systems, okay? We write a piece of C code to put on a microcontroller, and the C program, which is our engineering model, says nothing about timing. The timing is later determined by doing an analysis of a particular microprocessor architecture, doing worst case execution time analysis, building a scientific model of that microprocessor to try to figure out what the timing of that C program will be. That's a very difficult approach, and I think it's an approach that's ultimately doomed to fail. And for cyber physical systems, since timing is so important, we really need our engineering models to be very explicit about timing. Any implementation of the physical system is going to be correct only under some assumptions, right? If I give you an engineering model that says, particular calculation has to be done within 5 microseconds, then that implies some constraints on the physical realization. Under what assumptions will the physical realization meet those constraints? We need to make those assumptions explicit. Okay? Once we've made those assumptions explicit, we need to make violations of those assumptions detectable, because any assumptions we make about a physical realization can be violated in practice. The physical world doesn't always cooperate. Murphy's law kicks in, things happen. So, but you can't make violations of assumptions detectable unless you make your assumptions explicit. So that's a key observation, is make the assumptions explicit and then build in detection mechanisms. Now, there's a key role for scientific models. You can use scientific models to assess the likelihood that your assumptions will be violated. If you're assuming a particular bound on network latency, that's an assumption, okay? Use a scientific model of electrical propagation in a wire to determine whether or not your assumption about network latency is achievable, okay? That's a very simple use of a scientific model, and you can use that to build confidence in your models. Now, what about the mathematical relations between models? Well, you should use abstraction to expose flaws in your engineering models. Very broadly, this is the field that we call formal verification. So if I construct a C program, for example, that's a model of a behavior, I might then give you a linear temporal logic formula, which is another model, okay? And I would like that linear temporal logic formula to be a sound abstraction of the C program. And if the linear temporal logic program is specifying a requirement, okay, and I can't prove that that it is a sound abstraction of the C program, then there's a pretty good chance I have a flaw in that C program, and I can discover that flaw by discovering that the abstraction is not sound. That's what formal verification is about. What about refinement? Well, refinement can be used to manage complexity and to get what people like to call correct by construction design. Correct by construction is actually always a relationship between models. The physical thing is never correct by construction in any absolute sense. But if you think of, for example, what a compiler does, a compiler takes a piece of source code and translates it into a piece of target code. If the compiler is correctly designed, then the source code will be a sound abstraction of the target code, or put the other way around, the target code will be a refinement of the source code. And if the compiler is correct, that gives you a correct by construction translation between models. You take a higher level model, a more abstract model, you translate it into a model that has more detail, that is correct by construction in the sense that it is a refinement of the original model, or a sound abstraction in the reverse direction, okay? You can use abstraction to expose flaws in your engineering models, even without formal verification, even just at an intuitive level, right? If you write a C program, it's easier to understand. It's easier for a human to understand a C program than an assembly language program. So using a more abstract model, it's even easier to understand a higher level language, okay? Some functional language or a strongly typed language, which is easier to understand than a C program. So using more abstract models can be used to better understand your models. And then if you have correct by construction translations, you can get the detail through a synthesis process rather than through manual design. So let me talk briefly before closing about how I apply these principles in my research. And the reality is that even though I've never really, until very recently, in any way clearly articulated these principles, they've been kind of an undercurrent of the work that I've been doing for a long time. My latest research project is a project called Lingua Franca, which is a collaborative project. We're working with a very talented group of people, mostly in Germany and the US. In Germany, they're in Dresden and Kiel. And in the US, they're in Berkeley and Dallas at the moment, primarily. And this is what we call a polyglot coordination language. So it's a language for taking chunks of code written in a conventional pre-existing language and building components out of those chunks of code, and then integrating those components in a way that gives you explicit control over timing and concurrency, okay? So the particular target languages that are currently supported in Lingua Franca are C, C++, Rust, Python, and TypeScript. TypeScript is a type-safe version of JavaScript. So you write your program logic in any one of these 5 languages, and maybe there'll be more languages coming along. I personally would like to build a Java target, but we don't currently have one. You write your program logic using those languages. You pull in libraries from the ecosystem around which those languages live, and you then wrap your components written in those languages in what we call reactors. And reactors have timers that control timing. They have inputs and outputs for message passing between components. They have local state, so they do encapsulation of the state. And your composition of reactors exposes concurrency in the system, and it can be distributed across networks. So to give you a sense of how you could use this, so one of the key participants in this project is Sarush Bateni, who's a PhD student at UT Dallas, working with Kong Liu, which is working in a real-time systems group. So he took an open source self-driving car stack called AutoWare.auto, which is built using the robotic operating system, ROS, as the composition fabric. So he ported that entire stack to Lingua Franca using essentially the same component architecture that was used in ROS, but replacing ROS's component composition mechanism with Lingua Franca's component composition mechanism. Why do that replacement? Well, Sarush showed that, in fact, ROS works pretty well for this application. Pretty well, but not perfectly. In fact, he discovered a pretty interesting thing about this autonomous driving stack by running it on hardware that was typical of what it would be run on to control an actual vehicle. If he ran it a sufficient number of times, he found that anomalous conditions did arise in the system. In particular, he exposed a very interesting potential flaw where a piece of the control software could think that the transmission was in reverse and that the car is moving forward. Okay, so it's kind of a mode confusion problem, right? Because the car shouldn't be moving forward if the transmission is in reverse. And the reason that this component got into this mode, where it thought that that's what the state of the system was because of non-determinism in the publish and subscribe communication fabric in ROS. And if your network is lightly loaded and there's not a lot of contention for ROS, and the only subsystems you're running are these in AutoWare, then this mode confusion occurs quite rarely. Okay, I think he had to run several 100,000 runs before it showed up. So his claim is that the rarity of that anomaly is a more serious problem, because it means that it's very unlikely to show up in testing. And consequently, but when you deploy the system, of course, if it does get deployed in millions of cars and run for years, it will show up in the field. It's guaranteed to. And your system hasn't been designed to handle that kind of mode confusion. And as a consequence, you could end up with very dangerous situations. So the movement from ROS to Lingua Franca, the key property that gives you is determinism in the communication fabric. And that's been the key goal of Lingua Franca, is to show that you can actually build a communication fabric for distributed systems and for multi-core execution that is deterministic in the sense that the engineering model allows only one possible behavior, and the engineering model does not allow this kind of mode confusion. Okay? I emphasize this is a property of the engineering model. And when you deploy this on a physical system, the assumptions under which the physical system can deliver the behavior of that model are made explicit. So these assumptions do include things like bounds on network latency. But those assumptions now are made explicitly, and in Lingua Franca, there are mechanisms for detecting the violations of those assumptions and reacting to them. So you can build into your application code your fault handling mechanisms. And if this mode confusion occurs, it can only occur because of a violation of the assumption, and it's a detectable violation. And as a consequence, you can build your system to react appropriately to that violation. So this is kind of what a small Lingua Franca program looks like. It encapsulates verbatim target code in the target language. This particular example on the screen happens to be C code. So it's got these funny delimiters. Let me pull up my pointer. This curly brace equals surrounds a chunk of C code. This could be replaced with Rust or with C++ or with TypeScript or with Python. And then there's a composition layer that creates component compositions. And then there's a graphical synthesis that describes the structure of your program. This is derived automatically from the textual description of the program. And this graphical syntax was developed at Kiel in northern Germany. So the properties of Lingua Franca that are pertinent to this overall picture: it's explicit about a logical notion of time. It supports parallel execution on multi-core and distributed execution across networks. It guarantees, at the engineering model level, global ordering of related events. So if they're causally related events, they will always appear in the order that is specified by the program. It binds logical time to physical time at key points. So in particular, when there's interactions with the physical world, such as asynchronous events coming into the software system, then those events get time-stamped with a logical time that is based on the physical time of the event. The timing and determinism is respected under clearly stated assumptions. So if you build a distributed system, for example, with decentralized control, then you have to clearly state what your assumptions are on network latency, and violations of those assumptions are detectable, and you can build in to your application code your reactions to violations of these assumptions. One of my PhD students, Xiaokai Lin, is working on formal verification of these programs by building higher level abstractions on top of the Lingua Franca programs and showing soundness of those abstractions using techniques like SMT solvers and model checking. Interestingly enough, we get actually very high performance from Lingua Franca. You might be surprised by that, because many people assume that getting these nice properties like determinism have a cost in performance, but turns out our performance is competitive with the best state-of-the-art message passing systems out there. So let me just briefly elaborate a little bit more about this relation between logical and physical time, because that's a key subtlety. One of the issues with time, particularly in a distributed system, is that our naive notion of time, which many of us learned by studying Newtonian physics, it actually doesn't exist in the physical world. There is no instant. The notion of an instant in time that separates past and present is a fiction, okay? And in distributed systems, that the fact that that's a fiction becomes a real problem. It's an unignorable problem. So relating logical time and physical time becomes a kind of a key property of the art in these kinds of systems. So the idea of logical time is to give us a good, solid, intuitive engineering notion of time. Okay? It looks like Newtonian time. It behaves like Newtonian time. The physical realization of the system has to ensure that that behavior is like physical time. But when we want to relate the software system with the physical world, we have to connect some measurement of physical time to logical time. So for example, when an asynchronous event occurs in the physical world, for example, a robot arm touches something and the sensor tells you that it's touching now. Okay, there's an event there. You want to timestamp that event. You have to timestamp it using a local measurement of physical time. That local measurement is imperfect. It is not a Newtonian time. It is a measurement of time with all its imperfections. Okay, and you nevertheless can take that event and inject it into this engineering model view of the world, where it now has a logical time that does behave like a Newtonian time. On the performance issue, this is just a quick glance, thanks to Christian Minard of TU Dresden for the data. And the takeaway from this is comparing against two state-of-the-art actor systems, one called CAF and one called ACA. And the Lingua Franca C++ target is being compared against this with various multi-core implementations. And you can see that the purple bar almost always is at least competitive, often significantly outperforming these systems. We have some situations where those alternatives do outperform the Lingua Franca implementation. And we're working on, as we learn about these performance bottlenecks, we're using these benchmarks to try to drive performance improvements in the Lingua Franca program. But the key takeaway here is that achieving this level of determinism does not imply an automatic cost in performance. We're also working on a very aggressive project to get timing at the physical level to be exceedingly precise. And this is leveraging some prior work that my group has done on precision time microprocessors. These are microprocessors that can deliver very, very tight control of the timing behavior of the software down to nanosecond scales. And this is a work in progress to target these PRET machines using Lingua Franca. So these are the participants currently in the project. It's an extremely talented group of people. I'm really enjoying working with them. So in conclusion, engineering models are not the same as scientific models. That's perhaps the most important takeaway. You really need to know when you're working with a model, whether you're working with an engineering model or a scientific model. I derived from this picture, this audacious picture that binds together science, engineering, and mathematics, 6 principles of design. They're straightforward principles and pretty obvious, actually. Express all properties of interest, make your assumptions explicit, make violations of your assumptions detectable, assess how often your assumptions will be violated, verify your engineering models to expose flaws, and use synthesis of refinements to manage complexity. So with that, I would like to just point you to some references. The Lingua Franca wiki is currently the best way to learn about the language, and we'd love to get more people working on it. So please do not hesitate to contact me if you're interested in doing that. Thank you very much. I will stop sharing, and I'm happy to take questions.
Many thanks, Edward. A great talk as usual. Maybe if someone in the audience have questions. Yes, please, Sanjoy. Please unmute yourself, Sanjoy.
Yeah. Okay. Can you hear me?
Yes.
Okay,
Hi,
great.
Sanjoy.
Hi, Edward. Enjoyed the talk as always. I was curious about the point you made regarding the non-digital twin at the Airbus facility. What role does something like that have to play in, for example, the Lingua Franca framework? I mean, there's a basic inability to verify certain things, like the physical properties, for example. So how does that fit in?
So I think that's a very good question. And to be honest, I don't have a good answer. My hope, and at this point, it is really not much more than a hope, is that that those non-digital twins become unnecessary. Okay. And, I think that's a very aggressive goal. But if, at least one aspect of the digital twin does become unnecessary in this context, right? Which is having to have all the wires in your model be the same length. Okay. If you can abstract the length of wires as an assumption about network latency, and you can do that reliably, and you can be assured that as long as that assumption is met, the behavior is always the same, then you don't really need that physical twin to give you that property of latency.
But I thought the point you had made, and maybe I misunderstood, was that one of the reasons you need the physical model is because it's just too complex to be able to express all meaningful behaviors in a model. Like, the equations you need to solve are way too complex, and the physical device is doing it in itself. Is that not the rationale for a physical model?
That is the rationale if your mindset is still the scientific modeling mindset, where you need the model to accurately reflect the behaviors of the physical system. Okay, but if your mindset is an engineering model, then you don't need that anymore, right? You just need to ensure that your physical realization satisfies your explicit assumptions. Okay.
I see. So in essence, hybrid simulation is redundant because your engineering model will be instantiated in forms that are in the relevant forms faithful to the model is the assertion here.
Right. So let me give a concrete example of where this approach has proved successful in practice. Okay. How would you construct a scientific model of the Intel Haswell chip that I showed with 1.4 billion transistors? Okay. So one option would be to build a SPICE model of that. SPICE models on supercomputers can handle a few dozen transistors, right? Not 1.4 billion transistors. Okay, so that's not going to work. So you can't build a simulation model using SPICE of the Intel Haswell chip. Okay, the Airbus approach would be, if they were designing microprocessors, is they would build a physical twin, okay, with all the wire lengths the same. But that's a lot harder for a chip, right? Because the physical twin is actually just a chip, right? You don't, there's not anything to eliminate like there is in the aircraft, where you don't have to include the seats and stuff like that. There's no seats on a chip, right? So you don't want to construct a scientific model of the Intel Haswell. You construct scientific models of small, tiny pieces of it in order to validate that your engineering model assumptions will be met with high confidence. Okay, but then you validate your chip using an engineering model, not a scientific model.
Got it. Thank you.
Questions maybe from the audience, online audience? Then my turn to ask questions. I will ask about the lingua franca. So how is it easy to detect that the implementation of a library is incorrect compared to the coordination schema that was described in the in Lingua Franca.
So I'm not sure what you mean by the implementation of a library. You thinking of a library like the standard template library or something like that?
For example, you just call Python libraries and so on, and the behavior is not the one that is expected. How
Right.
is it? How much is it easy to say that it's a problem in the coordination itself, in the design of the coordination, rather than in the implementation of the library implementation itself?
Yeah. So an important thing to realize is because lingua franca is a polyglot language, it actually treats the target language code as a completely black box. The lingua franca compiler doesn't even look at the target code. Okay. And as a consequence, you still have to do all your validation of your target language code using the tools of the target language. Okay. So the compiler of the target language, for example, will check the type correctness of your system, right? That things are properly composed according to the data types. The lingua franca compiler doesn't even look at that. Okay. The only thing it looks at is the coordination layer. So the coordination layer is specifically about when a particular piece of target code will get invoked relative to when other pieces of target code get invoked. Okay. Those are the things that the lingua franca program expresses. And it doesn't do anything about whether the target code does something that is expected or unexpected, right? It leaves that to the target language domain to do that validation. So if you have a Python library and you call a function, you expect it to calculate an FFT and it calculates something else, lingua franca won't even know about that.
Then how the implementation of the language itself is assumed to be correct. I mean, how can you detect if there's something within the language or within the piece of code that are used? So is there a way to kind of debug or check or?
Yeah, I mean, you can use standard debugging tools for your target language. So you can invoke GDB, for example, on a generated C or C++ program and set breakpoints and do that kind of debugging. The kinds of things that do get detected by lingua franca are the ones that are the issues that have to do with orchestration, so and timing. So, for example, if you need a particular function to be invoked by a particular deadline, okay, then lingua franca will detect when that deadline is violated and will invoke a separate routine that you provide that is also in the target language, that is the deadline violation handler. Okay, so at the lingua franca level, that's all it does, right? It will either invoke the main routine that you specified, or it invokes the deadline handler if the deadline violation has occurred. Okay, but it doesn't say anything about what those two pieces of code do. What the deadline violation handler does is up to the application, right? It can be very application specific.
And then so if you consider the system, apart from checking the assumptions, if they are validated or not, you consider the final execution code as a whole, that you check for possible correctness, whether be it in the coordination as part of the system or the pieces of code that were inserted within the actor.
So Right. I mean, so a key part of the goal here is a separation of concerns, right?
Yes.
So, and, one of the principles underlying it is, my colleague Alberto San Giovanni Vincentelli likes to call it contract-based design, right? What you want is to wrap a piece of software in a contract, okay? And this contract says things like, well, in response to this stimulus, it'll produce this, stimulus on its outputs, okay? That kind of specification. And Lingua Franca is operating at that level, okay? It's, what is the stimulus coming into a component? What is the possible stimulus coming out from the component? And the messages between components are all logically time-stamped. And the Lingua Franca semantics guarantees that every component sees all events in timestamp order. Okay, that's the key guarantee. So if you have multiple inputs coming from a bunch of different sources, possibly scattered across the network, all right, if any two of those inputs have the same timestamp, you will always see them at the same time present, okay? If one of them has a timestamp bigger than the other, you will always see them in timestamp order. Now, when you actually physically realize the system, particularly with a distributed system, you face a fundamental challenge there, right? Which is, how do you guarantee that timestamp ordering? And there's a key theorem, which is due to my colleague, Eric Brewer, okay, called the CAP theorem. I don't know if you've heard of it, but CAP stands for consistency, availability, and partitioning, right? And what the theorem really says is that if your network breaks, you have to either give up consistency or you have to give up availability, okay? So in the Lingua Franca context, consistency is this ordering of time-stamped events, okay? So if your network breaks, if you want to guarantee consistency, you want to ensure that everything still sees events in timestamp order, you have to give up availability, which means that your system freezes. It stops working, okay? It doesn't do anything incorrect because it doesn't do anything. That's how you maintain consistency, is you give up availability. So we have two mechanisms for the distributed Lingua Franca, one of which emphasizes maintaining consistency. It guarantees that you will always see events in timestamp order. If your network breaks, it freezes. We have a second mechanism that guarantees availability. Every component keeps running, okay? Even if your network breaks. But that means you might sometimes see events out of timestamp order. That's a detectable failure, okay? And we can in fact guarantee that that failure will not occur if the network latencies are bounded, okay? But if your network breaks, your network latencies become unbounded, and then you have the possibility of seeing events out of timestamp order. So you use the second mechanism, this second mechanism that emphasizes availability in situations where availability is most important. So I can give you two very concrete examples in cyber physical systems. So imagine a braking assistance system in an ADAS, advanced driving assistance system in a car. So this is, braking assistance is using cameras and using analysis of the image to determine whether there's a pedestrian in front of the car or something else, right? That you want to apply the brakes. You also have a brake pedal, okay? When the driver pushes the brake pedal, you don't want to wait for your program to analyze the images to determine whether there's a pedestrian there. You want to just go ahead and apply the brake, right? You don't want the response to the brake pedal push to wait if the network is broken and you're never going to get the message from the subsystem that's doing the vision analysis. So that for that system, you want availability at all costs. You want to respond to the brake pedal regardless. Okay. The same kind of ADAS system, however, has another scenario where you have exactly the reverse requirement. So imagine self-driving cars that are cooperatively using an intersection. Okay. So now you want to make sure that no two cars are in the intersection at the same time. For that, you have to ensure that all cars agree on what the state of the intersection is. And consequently, you need consistency at all costs. If your network breaks, you want the cars to stop. You want to lose availability. You don't want them to just go ahead and enter the intersection, right? So for the braking system, you want to emphasize availability. For the intersection system, you want to emphasize consistency. You can't have both, right? You need to choose one or the other because of this CAP theorem.